Okay, great.
Yeah, so let me just introduce you first. Welcome everyone to this week's ICTS String seminar. We have Shreya Vardhan from MIT. She's going to talk about mixed state entanglement and information recovery in evaporating black holes. Over to you, Shreya.
Okay, great. Yeah, thanks a lot for the invitation to give a seminar at ICTS. And today I'll be talking about these two recent papers with Jonah Kadleflam, Hassan Shapurian, and Han Liu. Okay, so let me start with two kinds of motivations for this work. One set of motivations comes from just wanting to better understand thermalization and quantum information. So consider some chaotic quantum many-body system, which is initially in an out of equilibrium pure state, psi 0. Then in general, at late times, we expect that the system thermalizes, which means that the details of this initial state should be forgotten, and macroscopic properties of the time-evolved state can be approximated with some equilibrium density matrix, which I'll call rho equilibrium. So this means in particular that if I look at expectation values of local observables in the time-evolved state, then those should be close to the value in some equilibrium density matrix. But to learn more about this late time state, we can ask more fine-grained questions. So we can go beyond such expectation values and use information theoretic quantities. For instance, we can learn about correlations between different parts of the system by looking at measures like mutual information and logarithmic negativity. And due to unitarity, such information theoretic quantities in psi of t will not be equal to their values in rho equilibrium. Okay, so then the question is, can we still express information theoretic measures in psi of t in terms of rho equilibrium in some way? And if we can do this, then what is the resulting universal behavior of such quantities in this state? Okay. So a second set of motivations comes from wanting to better understand black hole dynamics. And in recent years, there has been strong support that black holes can be treated as examples of strongly chaotic quantum many-body systems. So in particular, the formation and evaporation of a black hole can be seen as an example of the process of thermalization. If you start with some isolated star, which is in a pure state psi 0, then under its gravitational dynamics, it collapses to form a black hole. And then at late times, the black hole emits some thermal radiation. And this thermal radiation knows very little about the details of the initial state of the star. So this is an example of thermalization. And so we can use universal properties of chaotic quantum many-body systems in order to make predictions about black holes. And this is something which can be very useful because the verification of these predictions can then confirm that black holes obey the usual rules of quantum mechanics. And in the process, we can also discover new features of quantum gravity. Okay, so let me give you a very famous example of this kind of logic, which is the page curve. So as a very simple model for a state coming from a very chaotic unitary evolution, we can consider a random pure state psi in a finite dimensional Hilbert space. And Page considered the average entanglement entropy of such states in some subsystem, which you can call A. And this entropy turns out to have a simple dependence on the dimensions of A and A bar. So it just turns out to be the minimum of the log of dA and the log of dA bar. So now if we assume that the combined state of the black hole and the radiation is something that has been produced by a very chaotic evolution, so it's similar to a random pure state, then the evolution, we can make a prediction for how the entanglement entropies of the black hole and the radiation should evolve during the evaporation process. Okay, so this red curve is something like the evolution of the dimension of the radiation during the evaporation process, and the blue curve is the dimension of the black hole. So we expect from this formula that the evolution of the entanglement entropies of both the black hole and the radiation should just be given by the minimum of these two curves. And so it should initially increase, and then at some time scale called the Page time, it should start decreasing. Okay. So this is a concrete prediction for the entanglement entropies based on assuming a unitary and chaotic evolution. And the same kind of model for the state produced by a black hole can be used to ask other questions. For instance, we can ask if we initially throw some secret diary into the black hole and then start collecting its radiation, at what point would we be able to recover the initial state of the diary using the radiation? And then by similar methods, the answer to this question also turns out to be the same page time TP. So at this time scale, the information of the diary suddenly comes out in the radiation. Okay. So such predictions were made just purely based on properties of highly chaotic quantum mechanical systems, but they were recently verified using a semi-classical gravity approach. And this approach had certain new ingredients known as islands and replica wormholes. So, and this was discussed in these papers, among others. So indeed, in this whole process, we made a prediction based on general properties of chaotic quantum manybody systems. And while verifying this, we were able to both confirm that black holes obey the general rules of quantum mechanics and discover some new features of gravity. Okay, good. Any questions about any of this so far?
Just a general comment. I mean, these calculations are, I mean, I'm not sure there's really a distinction, right? Because these calculations are all done in the presence of a non-gravitational bar. So the clearest interpretation actually is that they're non-gravitational computations in some BCFT. I mean, in a real theory of gravity, the Hilbert space wouldn't factorize, and so these things would not really apply. So I just want to say that it is a quantum many-body system, and it's a prediction for non-gravitational theory, and one is verifying it back in the same setup. No? It's not a gravitational verification. I feel it's probably not relevant for your talk, but just in terms of the motivation.
Right.
I mean, just to make it more precise, in all of these setups, these computations always done in a BCFT, right? So it's an ADS black hole coupled to a non-gravitational bar, and then the computation is best defined in a BCFT. So it is a quantum many-body prediction that's verified in a quantum many-body system, I feel.
Right. Yeah, I guess. But so I guess the radiation is treated as a non-gravitating system, but the black hole part is still, it does have gravity in these setups.
Isn't it that if you take a BCFT, then that part is, I mean, the whole thing has a representation as a BCFT. Like it's a, just a CFT on a space with a boundary. I mean, it's a very nice computation. It's really nice that one can compute these BCFT quantities using a gravity dual. But I'm just saying, and that's really great. But I'm just saying that it is a BCFT, and so the gravity is like a tool to compute a quantity that's well defined in the non-gravitational theory, which is great. Anyway, please continue.
Right. Yeah. At least. Yeah. Okay. So at least this can be seen as some kind of as you said, you are using semi-classical gravity in the calculation and the quantum extremal surface formula. So I guess the interpretation of it definitely needs more understanding, but it can be seen as some evidence for this formula based on gravity. And it did reveal these kinds of new structures in the process of trying to show it. So anyway, so for today's talk, I wanted to...
Just to make a comment, maybe a non-controversial example, maybe this page curve we can go back and forth about, but the spectral form factor, I think everyone will agree that the ramp that you compute you can make a prediction from, general theory of quantum chaos. And the double cone geometry is just a purely geometrical object. Like there is no bath or anything. So just another in the same spirit, but which doesn't have this objection that Subrat pointed out.
Sorry, Raghu, I got disconnected. Can you please repeat once again? I'm really sorry.
If you don't consider the page curve, but just consider the spectral form factor. So there is no bath or anything. Arguments by Berry and so on and quantum chaos people, no gravity involved, will tell you that there has to be a ramp. And Saad, Shankar and Stanford showed how to get the ramp purely from gravity. And that involves a similar kind of wormhole connecting the two sides. So there, none of these objections come in. So the point, I think, is still okay.
Thank you.
Yeah, thank you. That's a very nice, completely different example from this.
Ma'am, I had a question, ma'am.
Yeah.
Am I audible?
Yes.
Okay, so how does the page time and the page curve have any effect on the S matrix of the black hole? Will it have any effect? that if the black hole has gone beyond the page time, the S matrix will change somehow for the black hole?
I guess, so I don't know very much about the S matrix, and I think that is a different way of testing for unitarity from the page curve. Yeah, I guess, yeah, I'm not sure. Yeah, so this is a more kind of information theoretic approach to unitarity, and I think the S matrix, yeah, I'm not very sure of exactly how much of that is known from, like, how to calculate the S matrix directly from the gravity perspective. I think that's probably been done more from the perspective of the CFT.
So just maybe one comment on that. I don't know this paper very well, but there was a paper by Nawa Gaddam and one collaborator that was computing some S matrix, like two to many S matrix, and finding some signatures of the page time in that S matrix. So I just want to flash that paper, so that might connect these ideas.
Yeah, I think that would be pretty interesting to explore. I don't know much.
One of the authors is Nawa Gaddam. I can't remember the other person's name. Sorry.
Okay.
Oh, thank you. Thank you.
All right. So for the purpose of this talk, we discussed understanding the entanglement structure on the basis of a quantity called the entanglement entropy. But it turns out that in order to better understand the entanglement structure and information recovery, we need to use quantities that go beyond the entanglement entropy, such as logarithmic negativity and Petz map fidelity. And I'll talk a lot about what these quantities mean later in the talk. But they provide some further information about the entanglement structure beyond entanglement entropy. And then another simplification in the calculation I described earlier is that these Haar-random pure states can be seen as a model for equilibrated pure states at infinite temperature. So for instance, this entropy that we find for the case where A is smaller than A bar is just the log of dA. So it's like the entropy of the infinite temperature canonical density matrix. Okay, but in order to understand the effect of energy constraints, and in any infinite dimensional system like a QFT, we need to consider finite temperature. Okay, so those are two ways in which it would be nice in realistic systems and to learn more about the system to go beyond Page's approach. So in this talk, we'll address both of these 2 points that I mentioned. And in order to do this, we'll use a method called the equilibrium approximation, which was developed in this paper a couple of years ago. And this method allows us to express information theoretic measures in a finite temperature equilibrated pure state, purely in terms of equilibrium quantities, and in a way that is consistent with unitarity. So it addresses that question that I asked on the first slide about whether it's possible to express such measures in terms of equilibrium quantities. And it also turns out to be efficiently computable. And this allows us to explore the structure a lot in many different examples. And on applying this method to the logarithmic negativity and Petz map fidelity, we'll find surprising information theoretic properties of general chaotic quantum manybody systems at finite temperature. And then we can use these universal statements about chaotic systems to make new predictions for the dynamics of evaporating black holes. Okay, good. So the plan for the talk will be to first describe the setup and the method that I'm using for studying entanglement structure. And in particular, I'll introduce kind of how the equilibrium approximation is applied to the logarithmic negativity, kind of very briefly, but hopefully you'll understand the general gist of what I'm doing. And then I'll hopefully focus a lot on the results for entanglement structure and also the results for information transfer. And while talking about both of these things, I'll also discuss the related implications for black holes. Okay, good. Okay, so let me start with the setup and method that we'll use for entanglement structure. So we'll consider some general chaotic system, and we'll consider some thermalized pure state psi t in the whole system. And we'll divide the system into 3 parts. and ask about correlations between two of the paths. So in general, the reduced density matrix on A1, A2 will be a mixed state. And this will require us to understand the properties of mixed state entanglement and the best way to study it. Okay, and in the evaporating black hole example, I just wanted you to keep in mind that we'll be thinking of A1 and A2 as parts of the radiation and B to be the remaining black hole. So indeed, the whole system is in some thermalized pure state, and just the radiation part would be in a mixed state. Okay. So in general, a lot of progress has been made in understanding bipartite entanglement in pure states, which is captured almost entirely by the entanglement entropy. But mixed state entanglement turns out to have a much richer structure involving a variety of different quantities. And it's much less understood, especially in many-body systems. So two useful quantities for understanding this mixed state structure, entanglement structure, are the mutual information and the logarithmic negativity. So we look at both of these quantities and we'll vary the relative sizes of these three subsystems, A1, A2, and B, and use the equilibrium approximation to find both the mutual information and the negativity between A1 and A2. Okay, and as we vary these sizes of the subsystems, we'll find some qualitative changes that take place in the form of both quantities. And these changes will be referred to as entanglement phase transitions. So we want to understand this phase structure. So first, let me give you a little more background about these two quantities and what they tell us. Okay, so the mutual information is probably the most familiar measure that is used for studying correlations between two regions in some state. So it's just defined in terms of the entanglement entropy, which is defined in terms of the reduced density matrix in this way. And then the mutual information just involves taking the sum of the entropies of the two subsystems and subtracting the entropy of the whole system. For pure states, the mutual information is a very good indicator of entanglement because an unentangled pure state is always a product state. And so for pure states, if the mutual information is non-zero, that is equivalent to the state being an entangled state. Okay, but for mixed states in general, an unentangled mixed state is a separable state. So it can be some kind of classical superposition of product states like this, where these PIs are some probabilities. And such a state has no entanglement. But if the number of states in the superposition is bigger than one, if the number of states in the sum, this classical mixture is greater than one, then we have a non-zero mutual information, even though the state is not entangled. Okay, so in this case, the mutual information is reflecting some classical correlations which are present in the state. So in general, we expect that this quantity reflects both classical and quantum correlations in the system. Okay. So this is the reason for introducing another quantity called the logarithmic negativity, which is defined by taking a partial transpose so if you have a density matrix in A1, A2, you can define the partial transpose in A2 by just swapping the indices of the original matrix in the A2 part. And then in general, this partial transpose is not a completely positive trace preserving map, which means that it can lead to some matrix which has negative eigenvalues. Okay, so a measure of whether or not the state has negative eigenvalues is the logarithmic negativity, which is defined by taking the sum of the absolute values of the eigenvalues of rho A T2 and then taking the log. You can check, one thing you can check is that if you have a separable state like this, then its eigenvalues are unchanged by the partial transpose operations. So in particular, they're always positive. Okay, so the negativity of a state like this will always be zero. And so the negativity being non-zero implies that the state is always entangled. And in this sense, the logarithmic negativity only captures quantum correlations. I guess one tricky thing is that it can also be zero for certain states which are entangled. So it's not a perfect measure in that sense, but it's a lot more computable than many other measures of mixed state entanglement. Okay, so this is the quantity that we'll be using.
I have a question. What about, does it obey other properties that you might expect for entanglement? Like, you know, like you can't change it using LOCC, or it's monotonic under LOCC?
Yeah, I think that is true. Like, I think it obeys most properties that are required for entanglement measures.
I see. So the only problem is that you might have a state which is entangled, and this might give 0 somehow.
Mm-hmm. Yeah, that's right.
I see. But if it obeys that, I mean, maybe you could just define it as a measure of entanglement. I mean, you know, maybe it gives you 0 and some slightly unusual measure of entanglement. But you're saying if it obeys monotonicity under LOCC, then I see. Okay.
Yeah.
Okay. Thank you. Yeah.
I think that any state which doesn't have this form is entangled in the sense that it can't be given, like the correlations in it can't be given a hidden variable description and so on. So yeah, I think we really want to define any like entangled states as states, all states which are other than these ones. Right. Okay, great. So so in practice, we can use this measure. And then in order to actually calculate it, the quantity that we apply the equilibrium approximation to are these higher moments of this partially transposed density matrix. So you can take its nth power and take the trace. And these can also be used to define quantities called Renyi negativities, which are analogous to Renyi entropies, which I'll talk a little bit about later. But yeah, so you can, once you have these nth powers of the partially transposed density matrix, then in principle, you can use analytic continuation to calculate the logarithmic negativity from these quantities. But it turns out that in the calculations we'll do in practice, the analytic continuation will turn out not to be reliable in finite temperature cases, essentially because the different ends will have different behaviors in many situations. But a more reliable method for extracting the logarithmic negativity from these quantities is to use something called the resolvent, which can be used to directly extract the density of eigenvalues. And essentially computing this resolvent involves doing this infinite sum over all the ZNPTs. Yeah, and really the physically interesting quantity, the most physically interesting quantity out of these will be this logarithmic negativity, because it's the one which has the best operational interpretation, as I'll discuss later. Yeah, so this is really what we want to calculate. Okay, so how do we apply the equilibrium approximation to calculate a quantity like this? So let me just give you a little bit of a sense of how it works. So our starting point in this approximation method is to identify some equilibrium density matrix, which this psi of t resembles macroscopically at late times. So this choice of the reduced density of the equilibrium density matrix will just be an input of our calculation. And essentially different choices of this rho equilibrium will correspond to different universality classes of equilibrated pure states. So for example, we can choose rho equilibrium to be a canonical equilibrium density matrix at some temperature, and then different temperatures would correspond to different universality classes. And you can also look at a microcanonical ensemble and so on. Okay, so if you just write out explicitly what this time evolved quantity is in terms of the initial state and the time evolution operators, then it can be interpreted as a Lorentzian path integral on 2n copies of the system, just from the usual way that you turn these amplitudes into path integrals. And the initial state in this path integral on 2n copies will be determined by the actual initial state. And the final state is determined by the kind of pattern of traces that we want to take in this expression. Okay, so it's just something which tells you how to identify the different indices. Okay, so you end up with some expression which has some boundary conditions determined by the initial state and the pattern of traces. And then inside the path integral, you have some sum of phases, which looks like this. So you have a factor of S phi for each forward going contour and minus S phi prime phi I for each backward going contour, okay? And then one thing that you can notice in this expression is that this exponent vanishes in some special set of configurations where you set the fields on each forward going contour equal to the fields on some backward going contour. So you can just see that that vanishes because these always come with minus signs, okay? So such configurations will always give time independent contributions. And then a very heuristic intuitive idea is that all other kinds of configurations will give some large set of fluctuating phases, which should cancel out with each other at late times in a chaotic system. So somehow the sort of stationary contribution on average at late times should be given by the contributions from this set of configurations. So, but if we, and essentially you get one of them for each element of the permutation group because you can set the fields on each forward going contour equal to any backward contour, and this cancellation still happens. Okay,
sorry,
but if,
could you say where the partial transpose is happening in this path integral? Like,
yeah. So the partial transpose essentially corresponds to sort of how you should identify some of the initial and final conditions in this expression, right? Like between these.
Yeah. So what does it mean in terms of these phi I and phi I primes? Is there a?
So it just corresponds to some boundary condition on this side, on the phi i's and phi I primes between different.
Okay, so that has not been made explicit. I'm just trying to understand because so that identification is not explicit in this diagram. Is that right? Or
yeah, that's right. It's not, because it would be somehow in how you would connect these contours. Like I would divide each of these into 3 parts corresponding to A1, A2, and B. And then for B, I would just identify the ones on each copy. And for A2, I would do something more complicated because of the partial transpose.
Okay, thanks.
Yeah.
Sorry, just a question here. In the equation in this slide, the equilibrium state, the universality class is not so far important, right? This expression for the partial transpose is just an exact expression, right?
Yeah, exactly. Yeah, I haven't done anything using this this equilibrium density matrix yet. That's
fine.
Right.
Okay, thank you.
Yeah, but the reason you need to do something with that is that if you just put this expression into the path integral, then you get some divergent contribution, which doesn't make sense. So instead of this procedure, which I described, we do something a little more systematic, and that involves sort of projecting onto contributions which are associated with the equilibrium density matrix. I won't have time to go into the details of how to derive that, but essentially the expression that you end up with has this form where, again, I haven't explained what this notation is, but the main things that you should notice are that it involves the equilibrium density matrix, and it involves a sum over permutations. And the purpose of this slide was to give you some intuition for why it involves a sum over permutations.
Sorry, this I haven't understood at all. At some point, this equilibrium density matrix might be a good thing to look at certain observables, but why is it a good thing to look at the partial transpose? I mean, in a fine grained sense, it's very far from whatever a true density matrix you have. Right? It's, I mean,
absolutely. And so one thing that you can notice from this expression is that because of this sum over permutations, well, you can't notice it because I haven't told you what the expression means, but essentially, if you look at the tau equal to identity, like if you look at the contribution to the sum from the identity permutation, then that is just the value of the ZNPT in the row equilibrium state. But then you also get contributions in this sum from all of the other permutations. And because of those contributions, this expression will not be equal to the value of the partial transpose in the equilibrium density matrix. So at least like that is consistent with your intuition that the answer should not be the same as in the equilibrium density matrix.
No, I understand, but I was more worried that I thought the partial transpose is giving you some very fine-grained information about the state, like you know, it's and that seems to be somehow yeah. So I'm concerned about how one can get that in some simple way. It seems to have like a lot of degrees of freedom, like e to the s degrees of freedom, and I'm concerned about where that.
Yeah, I guess.
I don't know if I'm making myself clear, but yeah. It's. I'm just worried there's a fine-grained quantity which is being somehow computed in some coarse-grained way, and I'm not seeing what assumptions have gone into that.
Right. Yeah, that's partly because I haven't explained the derivation of this. So heuristically, what we're doing is doing this kind of projection. Of course, you can still ask whether or not doing such a projection is justified or not. But we show some sort of self-consistent arguments for why it's justified. And then I guess this is partly an assumption that we're making, that if you have a quantity which is sort of self-averaging at late times, like these negativities or entanglement entropies, then even though it's a fine-grained information theoretic quantity, you can still learn about it in this time-evolved state using some equilibrium density matrix.
This I've not understood at all. If you just, let's say we just had a pure state, and you know, it's still true that at late times it goes to the microcanonical ensemble. I mean, one can just show it for all observables, but the entanglement entropy is 0, whereas the entanglement entropy for the microcanonical ensemble is just totally different. So how does one even see this? I mean, maybe you can ask the same question for negativity. If we just take some pure state, it's not entangled with anything else, but there might be some other state which looks exactly the same, which is entangled. So I mean, how do we see even that difference?
Yeah, I guess so. Maybe it helps that for the entanglement entropy in the setup that you're asking about, the answer that you'll get from doing this procedure will be like, if you look at some system, the entanglement entropy for some system A, then the entanglement entropy from this procedure will turn out to be the minimum of the thermal entropies in A and A bar.
Yeah, and sorry, what is A bar?
A bar is just the complement of A. So I think your concern was that if A is bigger than half of the system, then you expect that the entanglement entropy should not be the same as in the equilibrium density matrix.
Yes, that's indeed one. Yes. But
somehow what you get from this procedure, because of this sum over permutations, is you get the minimum of the entanglement entropies of the equilibrium density matrix in A and A bar.
I see. Is that clear in some simple way, or it's...
So that is, yeah, that is not immediately clear until I explain what this notation means. But essentially, it turns out to be like this expression. So somehow you have, so you have one permutation, which is the identity permutation, and this eta. So these things which are appearing in this bracket are also different elements of the permutation group. So this eta is like a cyclic permutation, which connects the different copies cyclically. And in this whole sum, you have the contribution from, okay, so if I were to write the expression for entanglement entropy instead of negativity, then I would just end up with like an eta in A and an E in B. And you can, essentially because of the sum over different permutations here, the expression turns out to be exactly symmetrical between A and A bar.
So can you prove that, like in a Haar-random state, if you average with the Haar measure, that this gives you the right answer for Haar typical states? Is there a sense which one can prove something like this?
Yeah, so if you put in the choice of rho equilibrium to just be the infinite temperature density matrix, so just like the maximally mixed state on the system, then indeed you get the same answer as for Haar-random states.
I see. Okay, thank you.
Mm-hmm. Yeah, and the idea is that now we can use the same, like this can be seen as a generalization of the Haar-random average to cases where you have finite temperature by using other choices of rho equilibrium. Right. Okay.
Sorry, can I ask a quick question, which is possibly related, but from a very sort of different background? I mean, can you say something about what exactly is your criteria for choosing rho equilibrium? Because I would have thought that, you know, you can choose rho equilibrium only if you can sort of match up local observables. I mean, even if I don't think about complicated things like entanglement and negativity and all that, does your rho equilibrium correctly reproduce, say, non-local correlations in psi of t?
You mean just expectation values of non-local
Yeah,
observables?
just expectation values of non-local correlations.
Right. I guess, so one thing that you can show is, like I mentioned, you need some self-consistent criterion to justify this approximation method. And you can check that indeed, if you have, so the result of the result of this method for expectation values of local observables will always be sort of what I had on the first slide, that the expectation value is just equal to the expectation value in the thermal density matrix.
Sure.
But of course, you expect not to be correct when, say, the operator you're looking at is bigger than half of the system. You expect that not to be correct in general.
Right. So then why does it work for quantities like in negativity?
Sorry. So the in the case where the operator is bigger than half of the system, it doesn't work, and also the self-consistent criterion for justifying the average fails in that case. But for, I guess, one way of justifying it is that the self-consistent criterion that I mentioned always works for the negativity.
So should I sort of think about a situation where the sizes of A1 and A2 are extremely small compared to B?
No, not necessarily. I guess what I'm saying is that we expect that, yeah, somehow the negativity is a self-averaging quantity at late times in the equilibrated state.
I see. So it's something special about the negativity that's going on here. Is that what you're saying?
Well, we expect it to work for any kind of information quantity which has this property that it reaches some stable equilibrium value at late time. So it should also be true for the entanglement entropy.
My understanding is that this is like a generalization of Petz results. So Petz said you look at the entropy and you could have computed it in one state, and it's kind of universal. And my understanding is that this is kind of saying something similar for the negativity, that you do a Haar average and you get this answer with the Haar average. And what is more, I think fluctuations as computed with the Haar average are small. I don't know if you computed. I mean, Page also did. He also computed fluctuations with the Haar average.
Yeah, exactly. So the self-consistent criterion I've been talking about is just looking at, say, something which is analogous to the fluctuations, which is just applying the equilibrium approximation directly to a product of two of these quantities, and then checking that that's close to, so you can do the same kind of projection in that combined setup. And then you can compare to like applying it to a product of the individual quantities. And you find that at least those two answers are consistent with each other, which is kind of analogous to checking that the fluctuations are small in the Haar average.
I see. Okay.
And that is not true. And that criterion fails for quantities where you don't expect the approximation to work, like these expectation values of large non-local observables. But some does work for things like negativity, like the Z and PT quantity.
Okay. Yeah. Thanks.
Okay. Great. So. So with this final expression, like I said, I haven't explained all of the notation, but the main things I want you to notice are that it involves the sum over different permutations. And also it ends up depending only on row equilibrium. And somehow in the procedure where I didn't describe the derivation, but the initial density matrix rho 0 drops out of this calculation. If you assume that the effective Hilbert space dimension is large, which essentially assumes that the partition functions of this equilibrium density matrix are large. Okay, so yeah, and like we emphasized already, the answer that you get from this is not equal to just the value of Z and PT in the equilibrium density matrix. It also has some other contributions which lead to answers which are more consistent with the whole state, the state on the whole system being pure, and so on. Okay, so like I mentioned before, what we want to do in this talk is vary the relative sizes of A1, A2, and B and see what happens. And essentially, as we do this, the dominant contribution to this sum, the main permutation which contributes, will change. And essentially, the different dominant permutations are what lead to the different qualitative forms of Z and PT. And this in turn will lead to different qualitative forms of the logarithmic negativity. Okay.
Sorry, Shreya, what's the notation? Etas are some fixed permutations?
Yeah, so etas are cyclic permutations which send n to n minus 1 and minus 1 to n minus 2.
And tau is just some arbitrary permutation.
Yeah.
And
right.
what is the notation rho equilibrium comma tau on the ket side?
Yeah, so I didn't want to go into a lot of detail about this, but maybe I can.
Okay, it's fine if you were not planning to. It's okay. Yeah, please go.
Yeah, so it's just some expression which looks like if you have some operator O and a permutation sigma, then you get some product of n copies of matrix elements of it, and then the way that you identify the indices. So this is some state on 2n copies of the Hilbert space, and then you identify the indices in like half of the copies with the other half using this permutation.
Okay, thanks.
Yeah, but maybe intuitively you can see why such things would lead to like expressions for entanglement. Okay. Okay, great. So good. So you can do this procedure. You get different dominant permutations, and these will give you different phases of the logarithmic negativity. And then, yeah, so I described this procedure for the ZNPTs, but you can also do exactly the same thing for these Renyi partition functions, which are just traces of rho r to the n. And so again, you'll get sums of permutations with different boundary conditions for each of these Renyi partition functions. And then these can be used to find the Renyi entropies of different regions out of these A1, A2, and A. And then they can be used to find the mutual information. And indeed, in the mutual information, again, you'll find that there are different phases for different choices, different sizes of A1, A2, and B. Okay, good. Any more questions about the methods before we talk about the results? Okay, great. So, okay, so the first thing that we can do is just take this equilibrium density matrix to be the maximally mixed state or the infinite temperature equilibrium density matrix. And as we already mentioned, the results that you get from this coincide with results from just taking a random pure state in this finite dimensional Hilbert space. So more concretely, we vary the sizes of these two subsystems by varying some parameter lambda, which is the volume of A1 divided by the volume of the full system A, and C, which is the volume of A divided by the volume of the whole system. Okay. So as you vary these two things, which give you the two axes, you find that there are three distinct forms that the mutual information and negativity take. And in this case, we find that the mutual information and the negativity have exactly the same forms. And the mutual information is just always twice the negativity in each phase. So essentially, these quantities are reflecting the same physics. So let me take some time to just explain what the forms are and what they're telling us. If you're in the region where C is less than 1/2, so the volume of A is less than the volume of B, then you essentially find that both quantities are 0. So they're not exactly 0, they have a 0 volume law contribution. Essentially the intuition for this is that in this setup, both A1 and A2 are entirely entangled with B, and so there's no room for them to be entangled with each other, okay? And then you can also consider another situation where A2 is bigger than the combined A1 and B systems. And in this case, you find that the entanglement entropy is just, the mutual information and negativity are both just proportional to the size of A1. And essentially this is happening because in this picture, both A1 and B are entirely entangled with A2, and there's no entanglement between A1 and B. So essentially there is as much entanglement between A1 and A2 as there are degrees of freedom in A1. Okay. And then if you're in neither of these two regimes, so you have a situation where all three systems are of roughly the same size, then you have this more interesting pattern where both the mutual information and negativity depend only on the full size of A and not on the individual sizes of A1 and A2. So essentially what is happening here is that some number of degrees of freedom in A are used up in entanglement with B, and then whatever is left is just used for entanglement between A1 and A2. Okay, so you get these three qualitatively distinct forms, and they can be understood sort of simply in terms of some kind of bell pair-like picture. Yeah, and then the important thing here. Yeah.
So like if I was just looking at just entropy, like would it be true that entanglement entropy, would it be true that this dependence on lambda, dependence on C wouldn't be there? Is that right? Because I'm just asking in the sense like to make a density matrix for A, I thought I would just need a another system of size, same size as A, and I could purify A and then trace out the auxiliary part to get the density matrix of A. I'm not appreciating the dependence on how big B is on the mutual information of A1, A2, and so on.
Right. So it's essentially because you don't have a pure state on A. So you could have just expressed all of these answers in terms of parameters which are intrinsic to A. For instance, in this case, the log dB is just will just be the entanglement entropy of A. But does that make sense?
So can I, maybe I should rephrase my question. My question is like, I'm just looking at properties intrinsic to the system A. Yeah. And I'm not really appreciating why is it so, once I have the density matrix for A, how does it really depend on what did I trace out? How big B was related to A?
Yeah. So in this case where A is bigger than B, for instance, this log dB can be seen as the entanglement entropy of the density matrix of A. So I chose to express it in terms of B, but I could also just have expressed it entirely in terms of properties of A.
Can I make a comment, Akhil? I think the point is that you're working with a random pure state on A1, A2, and B, all three systems. So the size of B is important because you will get the density matrix on A by tracing out B. So yeah, that's why it comes in, because the random pure, the ensemble is defined over the full three systems.
Okay, thanks.
Yeah. Okay, good. So yeah, so somehow in this case, like the entanglement between A1 and A2 is also telling you something about like how all three systems are entangled with each other. Yeah, and that is, as you say, because you take a random pure state on the whole system. Okay, good. So these are the results for the infinite temperature or random pure state case. So at finite temperature, we can consider a lot of different universality classes. But so this is kind of the finite temperature diagram for one such universality class, where we were able to calculate the negativity in all of the different parameter ranges. But the properties that I'll mention on this slide are just common to all the different universality classes that we checked at finite temperature. Okay, so now in this case, in general, you can take the equilibrium density matrix to be inhomogeneous between A1 and A2 and B. So instead of defining lambda and C like before, I can just describe it as the ratios of the equilibrium entropies of A1 and A, and of A and the whole system, respectively. And then one thing you can immediately notice is that the mutual information in terms of these redefined parameters will always have exactly the same phase diagram as in the infinite temperature case. So you get some qualitative modification of some quantitative modification of the values of the mutual information in these three different phases, but the phase boundaries are at exactly the same lines. And so intuitively, it's reflecting a very similar physics to the infinite temperature case. But for the logarithmic negativity, we find that we can get qualitatively very different things from the infinite temperature case. Okay, and one especially surprising thing, which we found in all the different cases we looked at, is that there can be a regime where the negativity is extensive. So that is the regime below 0.5, which is shaded in this picture, while the mutual information is still sub-extensive. So it's still in this NE phase in this picture. And this should be extremely surprising because, well, partly because of what I told you a couple of slides ago, that the mutual information reflects both classical and quantum correlations, and the negativity reflects only quantum correlations. So usually you expect that even quantum correlations can't be extensive in a regime where mutual information is sub-extensive. But here we seem to be finding that the mutual information doesn't capture certain kinds of quantum correlations. So these are some important counterexamples to the usual wisdom, and they seem to arise universally at finite temperature. Okay, so this was one sort of important result I wanted to emphasize. This seems quite surprising, but you can give some interpretations to what this means. And one way you can do this is by considering two operational measures of entanglement called the entanglement cost and distillable entanglement. So let me first just explain how to define these. Okay, so if you have some density matrix rho on A1 and A2, then you can imagine creating this state by starting with some number of EPR pairs between A1 and A2, and then applying just local operations and classical communication between A1 and A2 in order to construct this state. So if you try to do this, then there will be some minimum number n that you need to construct the state. And this can be called the entanglement cost. Okay. And then similarly, you can imagine doing the reverse operation, which is starting with your state rho between A1 and A2 and converting it into some number of EPR pairs using only LOCC operations. And then you find that there's some maximum number m that you can get out of the state. So this can be called the distillable entanglement. And for a pure state, it turns out that both of these quantities are just equal to the entanglement entropy of either of the systems. So this is also why the entanglement entropy is a particularly useful and intuitive measure of entanglement for pure states. But for mixed states, in general, you have that the entanglement cost can be greater than or equal to the distillable entanglement, and neither of them has to be equal to the negativity or mutual information. To the entropy or mutual information. So these are probably the most intuitive measures of entanglement to define operationally, but they turn out to be extremely hard to compute even for few body systems. So it's essentially, we don't know any way of computing them for many body systems right now. But they can be related to some of the quantities that I would like, in particular to the mutual information and the negativity through upper and lower bounds. So in particular, and then you can also define more refined versions of these costs and distillable entanglements, which I don't want to define in detail right now, but you can define the entanglement cost for some larger set of operations called PPT operations, and you can describe some exact version of the cost, which corresponds to preparing the state with zero error at every step. But anyway, you find that you can relate, like there's a certain kind of entanglement cost, which is lower bounded by the logarithmic negativity. And the distillable entanglement is upper bounded by 1/2 of the mutual information. Okay, so in particular, this means that if you have a situation where the negativity is much bigger than the mutual information, then a certain kind of entanglement cost is much bigger than the corresponding distillable entanglement. So this is telling us that in such situations, somehow the preparation of the reduced density matrix on A from EPR pairs would be a highly irreversible operation. And this is something which is sometimes referred to as bound entanglement, because it's entanglement that is present in the state, but you can't extract it somehow. Okay, and what we've learned from our result is that such bound entanglement seems to be universally present in reduced density matrices of the state at finite temperature. Good. Any questions about this part? Okay. Good. So now, everything that I said so far was just about general quantum many-body systems. And now we can talk about what predictions can be deduced about black holes from these results. So like I said, in the black hole case, you want to imagine that A1 and A2 are two paths that you've divided the whole radiation into. And you can ask, essentially by looking at the negativity or mutual information, you're asking when correlations between different parts of the radiation start to grow during the evaporation process. Okay, and essentially what we found from the phase diagram for the mutual information is that it was always starting to grow at this C equal to 1/2 point, which is also called the page time. So this is just the time at which the equilibrium entropy of the radiation is equal to the equilibrium entropy of the black hole. And yeah, so this is kind of why the conventional wisdom is that the entanglement within the radiation starts to grow at the page time, because we expect that all correlations are captured by the mutual information. But now yeah.
So maybe I can make my previous concern more precise here. So usually, you know, if you just switch off gravity in some radiation region, you'll get some, maybe you can speak of R1 and R2. But here, if I understand correctly, you want a tripartite factorization of the Hilbert space into B, R1 and R2. But that I mean, we know we'll run into many, I mean, it doesn't even obey strong subadditivity, right? So this is just the strong subadditivity paradox. So if you start assuming there's really a tripartite factorization of the Hilbert space, I mean, we know that runs into trouble. Because now this definitely is also going into the gravitational region. You can't put all three of them into the non-gravitational region.
Right. I guess I was only thinking of having R1 and R2 be in the non-gravitational region, but.
Right, but I mean, don't you want to study all of these measures at R1, R2 and some mixed state, because there's a B which is sitting, if I'm understanding correctly, I thought this B is like the B you had in your earlier picture, and R1, R2 are like A1 and A2.
Yeah, exactly. Yeah, so I have in mind that the whole system is some pure state.
Right, right. So, but this is assuming a tripartite factorization, but we know that even strong subadditivity doesn't work for this system. Like, it's not true that SBR1 plus S. This is just a strong subadditivity paradox, because you know that R1 is entangled with B, but R1 is also entangled with R2.
Right. I guess I'm just assuming that. Yeah, I guess I'm not going into that paradox and just assuming that somehow you can treat the combined system like an ordinary quantum mechanical system.
Okay. I guess, I mean, if you just said that you had some PCFT, as people say it, then you could just take some region near the defect, call that B, and call it R1 and R2. But that region near the defect would not be the black hole in some sense, because I mean, even the island proposal, you know, some part of B is described by R2. So whether it's all of B or some part of B, there would be there's some redundancy between B and R2. But yeah.
So I think maybe if you allow yourself to couple these non-gravitational bars,
yes,
B would be like the SYK system. So let's not think of in the gravitational description. B would be like the SYK, and R1 and R2 are like two halves of the wire. R1 is the left half of the wire and R2 is the right half of the wire. And the way to think about B is like the SYK part.
Yeah, that I agree. That's what I was saying, that B is like the defect and R1, R2. But then B is not the black hole in some sense. I mean, the black hole is also has descriptions from R2 and so on. R2
but that's sort of the language that has been used in the recent papers. So that's maybe just a flaw in the way papers have been written, but that's what people mean when they write B.
I see. Yeah, I agree. If you just think totally in the non-gravitational setup, the defect you can call B, and two parts of the rest of the system you can call R1, R2. Okay.
At least we can do that.
Okay.
But is it okay to think of B as the part of the black hole that is outside the island?
No, it should just be the entire black hole.
No, but Ashok might be right? That maybe the way B union R1 is the part of the black hole that's outside the island. B is probably something more restricted. because R2 is dual to the island, so B union R1 is something that's part outside the island, but it's yeah, B is some sub part of that.
Yeah, because I thought the part of the black hole that is outside the island is not encoded in R1 or R2, right?
Yeah, yeah. There's no black hole at all, because in many cases the island might just cover the whole black hole, but so there's some part of the bulk which is outside R2.
Okay.
Yeah. Okay. Yeah, that seems reasonable. Yeah. I guess, yeah, we want to think of B as like the quantum mechanical description of the black hole whose dimension will actually be decreasing during the evaporation process. Oh, so maybe that's only some part of the semi-classical picture. Okay, great. So yeah, so within this picture, so the usual time at which, so the time at which the equilibrium entropy of the radiation becomes equal to the black hole is called the page time. And this is also the time at which the mutual information between these two parts starts to become extensive. But what we seem to be finding now is that at finite temperature, the negativity between two parts of the radiation starts to increase at an earlier time scale, which we can call TB. And essentially it can be inferred from those diagrams that I showed earlier, that this is essentially a time scale where the 1/2 equilibrium Renyi entropy of the radiation becomes equal to the second equilibrium Renyi entropy of the black hole. So in any case with finite temperature, you can check that this time, just because of the usual inequalities between Renyi entropies with different indices, this time will always happen at some macroscopically earlier time scale than this time. Okay, so this is telling us that there's some entanglement within the radiation well before the page time, in contrast to what we usually think. So just to summarize, at infinite temperature, you find that both the negativity and the mutual information start to increase at the page time. And essentially both of these time scales just coincide in the infinite temperature case. But at finite temperature, you find that while the mutual information still increases at the page time, the negativity starts increasing at this earlier time scale TB. And somehow it seems like because of this characterization on the previous slide, the entanglement that is present in the radiation in this regime, it seems like it can't be distilled into EPR pairs. So it's some more mysterious kind of entanglement. Okay. Yeah, and I guess, so this also has some connection to replica wormholes. So I wrote down this expression earlier for what you get out of the equilibrium approximation. And each term in this expression can be seen as a Euclidean path integral on n copies of the system. So I haven't explained this, but it can. And essentially the boundary conditions with which you connect these different copies are determined by what permutation tau you have. And in holographic setups like this model of Pennington, Schenker, Stanford, and Yang, these Euclidean path integrals can be seen as boundary path integrals, which can be equated with some bulk path integrals. And then we find that the contributions which dominate in these phases with non-trivial negativity are contributions which have some replica wormholes. So essentially any term in this sum other than the identity permutation will lead to some replica wormholes between some copies. And this procedure is telling us exactly what kinds of replica wormholes we should include in the different phases if we were to do a Euclidean gravity calculation. But I guess one question to be explored in the future, which would be very interesting, would be whether the extensive entanglement before the page time can also be seen directly from some Lorentzian gravity calculation instead of going through this Euclidean picture. And then it would be interesting to see if you can find some new structures in semi-classical gravity similar to the island, which reflect these correlations that are present within the radiation. Yeah, so we don't know how to do that yet, but I think that would be very interesting to do. Okay.
I didn't understand the comment about the Lorentzian part. I understand that this quantity is probably some boundary conditions you can set up on the boundary side, and then you can fill them up with various geometries in the bulk. why is the Lorentzian versus Euclidean important?
Yeah, I guess I'm thinking of how, like, in the replica wormhole versus island calculations, when you do the island computation, you don't have to Euclidean picture, you're just using the QES formula.
You mean if there's a remnant in just the actual geometry of this entanglement?
Yeah.
I see.
Exactly. But somehow I think the problem is that we don't really know the holographic dual of the negativity. And so it's not clear what that picture would look like.
Right, but in any case, I guess if you did the Euclidean computation, let's forget about the island per se, but you might predict that there are some new kinds of wormholes with these boundary conditions, right? If you take the lesson that it's these non-trivial wormholes that are giving you, all the new stuff, quote unquote, then you might predict that, there's just some new wormhole with these boundary conditions that gives you those contributions.
Yeah. So we definitely have that already. It's just that we, so those are essentially like, they look different in the ES and ME phases. So the ES was the phase where you didn't have a dependence on the individual dimensions, and that.
So you can draw pictures of the geometries that kind of give you that part of the curve or that part of the region. I see.
Yeah, you can do that. So for instance, in one of the phases, you get like replica wormholes which connect adjacent copies.
Mm-hmm.
And then you can do that in two ways, essentially, if you have an even number of copies. And then, if you have, if you want to be in one of the phases, then you have to connect all the different copies. But we do have concrete descriptions of that.
Okay, thanks. Yeah.
Okay. Actually, so I am over time. I don't know when I should stop, or I have like 3 more slides after this.
Sure. Yeah. We can go on for maybe 10 more minutes also. That's fine.
Okay, great. Okay. So, so now let's ask just a kind of different question from the one that I've been asking for most of this talk, which is about an experiment where we imagine throwing a diary into the black hole. And then at some later time, after the black hole has been emitting some radiation, I collect all of the radiation and then try to deduce what was the state of the diary that I threw in. Okay, so this whole evolution of the diary together with the black hole can be seen as the following quantum channel, where I just take the initial state of the diary, I tensor it with some fixed initial state of the black hole. It undergoes some unitary evolution. And then at later times, I lose access to the remaining black hole. So the output is just on the radiation. Okay. And if I want to retrieve the information of the diary, which is essentially, I want to figure out what this initial state was, then I can see this as an attempt to reverse this quantum channel. Okay. Now, given any quantum channel, I can always write down a recovery channel which attempts to reverse it, called the Petz map. And so in this setup, we would have some explicit expression for the Petz map for this channel, which would take us from R to some Hilbert space, which has the same dimension as the diary. And of course, this won't always work. So in cases where I can't recover the state, I'll just get a very bad answer from doing this Petz map, which will have nothing to do with rho d. But in cases where it works, then I would find that it has some high fidelity with the initial state of the diary. So I can use the fidelity of the output of this channel as just a measure of how well I can recover the information. Okay, so if I have a small fidelity, then I have a small likelihood of recovering the information. If the fidelity is 1, then I have perfect information recovery. And again, so the Petz map has some explicit expression, which I haven't written down here, but that can also be evaluated using a certain replica trick. So again, that can be converted into a path integral, which involves some number of copies of U and some number of copies of U dagger. And so I can also apply the equilibrium approximation to this, just like I applied it to the negativity and the entropy. And again, I can do this in the finite temperature and infinite temperature cases. Okay, so we can consider two cases. We can consider a case where you have some small diary, which has some small number of degrees of freedom, or you can have a case where you have some large number of degrees of freedom in the diary, which are comparable to the sizes of the black hole and the radiation. Okay, so we'll consider the cases of the small and large diaries and the zero temperature, and the infinite temperature and finite temperature cases. And in all cases, what they have in common is that the fidelity starts from some value which is exponentially small in the diary size, and eventually it saturates to a value of 1. So initially the information recovery is very bad, and then as we expect, as we collect more and more radiation, eventually we can recover almost perfectly well. Okay, but the way in which it evolves is kind of different in all of these cases. So let's first focus on this infinite temperature case, where this known result of Hayden and Preskill tells us that if you have some small diary, then the information comes out suddenly at the page time, okay, or very quickly at the page time. But now if you look at this, so the fidelity goes from its initial value to 1 in a very short time scale. But now if you consider the case of a large diary and you look at this fidelity, then you find that you get this kind of exponential improvement starting at the page time. And eventually it saturates to 1 at some new time scale, which is defined by essentially as a time scale where the entropy of the radiation becomes equal to the equilibrium entropy of the black hole plus the size of the diary. Okay, so this was earlier identified in some papers about alpha bits as a time scale where the recovery becomes almost perfect. And one nice thing about our calculation using the fidelity is that you can also see that there is some gradual improvement of the likelihood from this small value to a value of 1. Okay, but so far this is nothing surprising. So this all seems quite intuitive. But now if you look at a case where you have finite temperature, then if you have a small diary, then again you find that the information comes out quite rapidly at the page time. But if you look at a large diary, then you see this extended improvement of the fidelity from a small value to 1. But the time scale when this fidelity starts to grow is actually this same earlier time scale TB, where the negativity between different parts of the radiation started to grow. And in particular, it's earlier than the page time. So somehow, like we did essentially a completely different calculation for this quantity, but we seem to find the same time scale emerging from this other calculation. And this seems intuitive because somehow the fact that there are some quantum correlations present in the radiation does seem to indicate that there's some non-trivial information in it. But it can be made kind of more operationally precise using this calculation.
I have 2 quick questions. One is, is TB just some order 1 fraction of TP, or is it something smaller? Like, is it 50% or 80% of TP, or what is the?
Yeah, so it should be some order 1 fraction of.
I see, some order 1 fraction of TP.
Because it's defined as that time where the 1/2. So essentially this parameter C can be seen as some standard, like the parameter C that I had in the diagram can be seen as some stand-in for the time. So you have some kind of small order difference between them.
The other question I had was, so in these kind of Hayden-Preskill recoveries, usually you get the diary a bit later, like you get it at like e to the s black hole times how big the diary is, right? Times the dimension of the. So is your T page here defined to include that factor of the diary size or not?
Yeah. So that's what I'm defining this TP2 as. So that is defined by this condition, which I think is exactly.
Okay.
So that is when it becomes close to 1. And then for a small diary, I'm just assuming that both of the timescales are just the same.
I see. Okay. Thank you. Yes.
Right. Yeah. Okay. So somehow, the main point here was that there's this same time scale emerging if you look at the fidelity. And of course, this leads to a lot of new questions. So I guess, entanglement wedge reconstruction essentially corresponds to a case like when the fidelity is close to 1. So we don't really have a quantity on the gravity side which is able to detect, or so far that I know of, we don't have a quantity which is able to detect this kind of exponential, this gradual improvement of the fidelity. So it would be nice if there was some way of identifying some gravity dual of this quantity, and then we could see this gradual growth of the fidelity, which begins before the page time at finite temperature. Another interesting thing is that there is a known lower bound on the fidelity of some recovery map. So in particular, something called the twirled Petz map, which is slightly better than the Petz map, always works. And you can give a lower bound on the fidelity of that map in terms of the difference in relative entropies before and after applying the channel. Okay, but that difference in relative entropies is also something that you can compute using the equilibrium approximation. And for that quantity, somehow we find that it only starts to grow at this TP timescale, and it doesn't seem to be sensitive to TB. But like I mentioned, this TB was also the timescale at which the negativity between different parts of the radiation started to grow. So it would be interesting to understand if, just purely from an information theoretic viewpoint, if there's some sort of general connection between measures like logarithmic negativity and the ability to perform information recovery. So the only thing, so far we don't have any kind of understanding of that from an information theoretic viewpoint. It's just that we have these two calculations which give the same time scale. So this would be very interesting to understand in the future. Yeah, I guess I can just end with that. So thank you for listening and for all your questions.
Thank you, Shreya. Let's all thank Shreya for a nice and.
Ma'am, I had a question. Am I audible?
Yes.
Yes, ma'am. So does the relative volume between the black hole and the radiation have any kind of signature in the holographic complexity?
Yeah, I think so. So that is not related to. So there is no direct connection between any of the quantities that I was talking about today in complexity. I think there are some known connections. So sorry, do you mean like in this talk, these different volumes that I'm referring to, if they have any connection to the complexity?
Yes, ma'am.
Somehow the volumes that I'm talking about are not really geometric objects. I've kind of been using just the quantum manybody perspective. So the volumes are more like just logs of the dimensions of the different subsystems. So none of the things that I talked about have any direct connection to complexity.
Okay, but fine. But if we consider all the replica wormholes and their growth, will that have some kind of holographic connection? Would that have some kind of complexity connection? All the different replica wormholes.
Yeah, so I think that is kind of one of the questions that people are trying to understand, if quantities like entanglement entropies have some connection to measures of complexity. So in principle, yes, but I don't know any concrete answer to that.
Okay, thank you.
Okay, right. I have a question. So it's a very elementary type of question. We know that in continuum quantum field theory, the entanglement entropy is divergent, has an ultraviolet divergence coming from the boundaries because of the short distance modes. And in the island formula also, we know that this very beautifully, the two terms, the ultraviolet divergence cancels and one has a finite answer. This also depends, this also happens for the mutual information. I can imagine that the ultraviolet divergence cancels. For this new diagnostic you mentioned, this logarithmic negativity, do you know whether this is ultraviolet finite, this object?
Yeah, that's a good question. There have been calculations of the negativity in quantum field theory. I don't actually know whether, I expect that it's not, because it also kind of relies on a tensor factorization of the Hilbert space.
Yes.
To find the partial transpose.
Yeah.
Yeah, but I don't know immediately.
Okay, thank you. Thanks.
Yeah, I have one question, which is when you define the page time for a large diary, is this the page time by taking into account the effect of the diary into the black hole, or is it the original black hole page time?
Yeah, so it's exactly the page time that you get from including the diary in the black hole degrees of freedom, essentially. So it's defined by this condition. So this is just when the entropy of the radiation becomes equal to the entropy of the original black hole. So this was without the diary, but then you add the dimension of the diary.
So that's you're defining as the page time.
So this is what I'm defining as TP2. And I'm still defining TP as when the radiation entropy is equal to the black hole entropy.
I see, okay. Okay, thank you.
Are there any other questions for Shreya? Well, if not, let's thank Shreya again for a wonderful talk.
Okay, great. Thanks a lot for all the questions.
Yeah.
All right.
Thanks for making the time in the morning.
No, of course.
Yeah,
Thank you for having me.
Take care. Bye-bye.
Okay.
Bye.
Bye. Bye, everyone. I'll close the call now.